I'm currently in Germany, so good afternoon, I would say. My name is Joost Pieter Katoen, and I am leading the group on software model checking and verification in Aachen. And today I would like to talk about how to scale analysis of fault trees by using model checking. So my plan is to actually, I divided the talk into 5 parts. I will start off with classical static fault tree analysis. I hope that's for most people that you are familiar with this. And then I will also recap what is the current state of art there. Then I will introduce to you a model called dynamic fault trees, and I'm going to justify why this is an interesting model. And then in part 3, I'm going to present briefly a couple of techniques that allow us to actually analyze all kinds of reliability metrics of very large, I would even say huge dynamic fault trees. This has all been implemented and be realized in a software tool that we're going to demo in part 5, and that will be where Falak Shah will take over. And what I will show you in part 4 is actually 3 different industrial case studies where these techniques have been applied. So reliability is important for different kind of systems, right? I mean, airplanes, satellites, but also, for instance, water treat systems. The analysis that I'm going to show you will be illustrated by 3 industrial examples, one concerning railway infrastructures, one concerning automotive, driving, and the third one will be power supply of nuclear power plants. And I would like to show you that I'm going to make my argument, and that will be the bottom line of the presentation, is that you can faithfully model the reliability of these kind of systems using dynamic fault trees. And although these systems are complex, you can analyze them fully automatically using state-of-the-art tools. So that's basically the bottom line of my message. So I would like to start with something that is familiar to you, right? I mean, we all know risk analysis, where you ensure that certain critical assets, like medical devices and other devices, operate in a safe and reliable way. And fault tree analysis is, since the 1960s, is already one of the most prominent techniques there. It's used by many industries. It's used by many institutions, and actually it's also standardized by industrial standards, for instance, by the International Standard Organization, ISO. There is this ISO 26262, which actually explicitly requires automotive applications to apply modern fault tree analysis techniques. So fault trees are even used in SpaceX. That was in 2015 an explosion of one of the attempts of the company of Elon Musk. And when this unfortunately failed, he was actually using Twitter. And on Twitter, he was even saying, well, there was a kind of an overpressure event, and data suggests some counterintuitive cause. And at the moment, we cannot really say with confidence what exactly happens. And what we will do is we will follow this by a thorough fault tree analysis. So even Elon Musk in SpaceX is using fault tree analysis. So what are fault trees? And these are the original fault trees that date back from the 1960s when Watson developed them at IBM. So a fault tree is nothing else than a directed acyclic graph, where you have basically events. They model the kind of failure of standard components. And then you have gates, and gates basically model how to propagate the failure through the system. And in static fault trees, you have AND gates, you have OR gates, and you have voting gates and some other gates. And what you typically have are basic events, which you can view as the kind of the leaves in the tree. And then basically you're interested in when does the root of the graph or the root of the tree fails, because that models the system failure. Yeah, so here is an example of a small model on the left, where you see a computer. The computer consists of a couple of workstations. Every workstation consists of a computer and a power station. And the two workstations, W1 and W2, they share a memory. And the memory is modeled by a voting gate. The memory is failing when 2 out of 3 of its memory modules are failing. Now, how can you analyze these kind of fault trees? What you do is you compute a set of components that is sufficient to cause the system to fail. And typically you're interested in what is the minimal set of components that is, let's say, necessary to the system to fail. So in the left picture, you see indicated by dark blue that this component B there, if B fails, then actually the OR gate C fails, and then the whole system will fail. So B is what they call a minimal cut set. B, the failure of B leads to a system failure. Similarly, when all the let's say the memory modules at the bottom of the fault tree fail, then of course also the whole system will fail. But this is not minimal because it suffices that 2 of the memory modules will fail. And on the right-hand side, you see this exemplified by, for instance, M1 and M2 being failed. And minimal cut sets are basically the key ingredient to analyze fault trees. So how to analyze such a fault tree? The basic recipe, and I don't go into all the details, is that you take a fault tree, see the picture on the left. A fault tree is nothing else than a Boolean formula. So you can basically interpret this picture as a Boolean formula.
Sorry, Professor Canton, we are still on the title page. Are we sharing the right screen?
This is bad.
No, I can see the slide that you were showing, Professor.
Oh, okay.
I can also see the recent slide.
Okay, I will try to do it again, right? Let me check. I now reshared the slides, and you should see a colorful picture.
Yep, the slide title is SFT analysis.
Exactly.
And there are 3 graphics, 3 illustrations on the slide.
Exactly. Thank you. Yeah, that's exactly the slide. So we have a static fault tree on the left. It's not very important to understand exactly what it models, but the idea is that you interpret this static fault tree as a logical formula. And then the main issue is how can you succinctly, so very compactly, represent such a formula. And this is known already from the 1950s that you can use binary decision diagrams. And I showed you 2, one in picture B and the other one in picture C. What's the difference between them? And you see it in the different order of the colors. It's the ordering basically of the leaves of the fault tree. In the first one, A is in the top, and then the right one, C, is on the top. And actually, it's well known that this ordering has a drastic impact on the size of the BDD. You see here that the right BDD is a bit smaller than the one in the middle. All the state-of-the-art tools for static fault tree analysis compile a static fault tree into a binary decision diagram. And then on top of this, they do all the calculations. So they can very efficiently calculate the minimal cut sets, the mean time to failure, what is the probability that my system will fail within time t, availability, and even sensitivity like Birnbaum indexes and other kind of, let's say, importance measures. So here I show you some experiments in what you can do. And this is, as you see from the top of the slide, quite recent work. So here are some examples of static fault trees. You see in the table in the first row, basically several, let's say, different areas. Aralia is a standard, let's say, library of benchmarks. Sprinkler is a fire sprinkler system, railway industry, etc., and some randomly generated fault trees. And you see the size ranges from very small, let's say, a few hundred, up to thousands of elements. And if you now use the tool that actually we are going to demonstrate later, then you can actually analyze them. And here you see some plots. And you see here the comparison of our tool, which you see on the y-axis, to 2 other tools. On the left, it's the tool Scram, which is an open source, a public available source tool for static fault trees. And on the right-hand side, you see XFTA. And XFTA is a part of the Alta-Rica toolset for analyzing fault trees. And the way to interpret these pictures is both the X and the Y axis are log scale. It means that any point on a diagonal, it means that both tools, the one on the X and the Y axis, are equally fast. But if the points are below, then it means that the tool on the Y axis is faster, right? So on the left, you see, for instance, on the dashed line, the first dashed line below the diagonal means the tool is 10 times faster. The second diagonal would mean then the second dash line would mean 100 times faster. And what you see from these experiments is basically that for computing these minimal cut sets, which actually is what these pictures depict, this state-of-the-art tool is actually quite fast, and in particular for large SFTs. For large SFTs, here you see on the left that, for instance, I have to go back. Sorry for that. On the left, you see in the picture some dots on the dashed line completely on the right, which means out of resource, which means either it's a timeout or it's a memory out. So those models are simply too large to be handled. Good. I see that my system is going in the wrong direction. Sorry for this. Now, SFTs have been used a lot. Their advantage is that they are very simple. They're simple to comprehend. They're also very simple to analyze. I just explained you this basically in one slide. But they're too simple to model realistic scenarios. So they do not have the support, for instance, to model spare management. Right? I mean, if you have elements that can fail and you have spares and you would like to replace a failed element by one of the spares, this is not possible to just model this. If you have common cause failures and you have lots of dependencies, then this is also difficult or even impossible to model using static fault trees. And redundancies you can model, but only in a very restricted way. The main limitation perhaps is that the behavior is fully static, which means that the failures or the faults are not temporally ordered. And that means that it suffices, as you have seen, to only know what is the set of events that has failed so far to know whether the whole system has failed. So the whole ordering of those failed events is not of any relevance. Now, this has given rise in the literature to many different variants. I just list a few here. What we are going to talk about is the last one, which is Dugan's dynamic fault trees. The other models actually share a lot of commonalities with this model. So I think this is really a kind of example of the other, let's say, variants of static fault trees. So dynamic fault trees have been developed in the 1990s by Professor Dugan. And you can read, they have extended the state of the art and the state of practice in analyzing dependability of computer systems. In the second line of the slide, you see the different gates. We don't have only ands and ors, but we have a couple of more gates. And I'm not going into the details here. I'm going to use an example so you illustrate it, hopefully somewhat easier to understand. And what perhaps is important later, if I show you experimental results, the very first tool, I think published in 1998, was the Galileo tool on DFTs. And what you will see in the rest of the talk is the enormous boost of performance since this time, using all kinds of techniques, in particular model set. So this is a dynamic fault tree. It's actually a static fault tree of a virtual meeting, a meeting in that like we have now, right? We use some software. We either use Zoom or Teams or WebEx. We use an internet via Wi-Fi or mobile, and we use a laptop, which is has either a hard disk or has a power, let's say, model. So the laptop can fail if the hard disk fails or the power fails, and the power can either be a plug or a battery. Now, using dynamic gates, you can model this more adequately. For instance, in the power, it's better to use a spare gate, where this is actually modeling that you can use a plug. If the plug fails, you can then use the spare, and the spare is a battery. And this is exactly what this gate models. Similarly, here with the internet connection, here, if you have a Wi-Fi connection, like I now have, it's all fine. And only if that fails, I can replace it with my mobile, for instance. So the mobile is my spare, and such a spare gate models very naturally spare management. Similarly, you can have common cause failures, like electricity. If the electricity fails, then my Wi-Fi will fail immediately, and my plug will fail immediately. And this is what they call a functional dependency, and you can easily model this in a dynamic fault tree. And finally, there's a gate called the priority end, where you see that the mobile phone fails if first the prepaid is empty and then the data limit has been reached. But if the data limit has been reached, but let's say the prepaid empty has not been reached, then I can still use the mobile. So here the ordering of the two children, the two leaves of the mobile phone are important. And that's the difference with a normal end. So dynamic fault trees have been around since 1990 and since the mid-1990s, and there have been quite some confusion about these dynamic fault trees. So here I just take two statements from two papers, not very old actually, that basically say, okay, dynamic fault trees are powerful. They have a very, let's say, rich possibilities to model dependability patterns, but the quantitative analysis is troublesome, especially if they are large and complex. And the second, let's say, which is an overview paper by Kabir on fault trees, it says, although many extensions of fault trees have been proposed, they suffer from a variety of shortcomings. In particular, their analysis requires a lot of manual effort. I'm going to show you that these are really myths. I mean, I'm going to show you that you can analyze scalable, huge dynamic fault trees of complex systems in a fully automated way. Good. And how to do that? We're going to use a technique called model checking. So schematically, it works as follows. On the left, we have a dynamic fault tree, and we have a reliability measure that we would like to compute. So for instance, here, the unreliability within a certain deadline T. Internally in the tool, so this is not that the user has to do, this is done automatically. The dynamic fault tree is turned into a state space. It's a Markov chain. Okay, continuous time Markov chain. And also internally, this measure, the reliability measure, is transformed into a logical formula. You don't have to understand exactly what it means. What we see later is that the use of logic under the hood means that you can cover many different measures, and not only the standard measures, but you can do much more. And these are the two inputs to what is called probabilistic model checking. And from that, it will generate analysis results. Now, you may ask yourself, this generation of a Markov chain from a fault tree, these Markov chains can be huge. So this will not work for large DFTs. And we're going to see that this indeed is not exactly true. And I'm going to show you this by means of this example, which is a hypothetic DFT proposed by Dugan. So about 10 years after she introduced DFTs, and where she literally said this example was created to make the Markov chain drastically large and practically impossible to solve without resorting to simplifying assumptions and or approximations. And indeed, if you are not careful and you generate the state space in a naive way, you get about 60,000 states, and the analysis is about a second. The techniques that we use and that are called optimized state space generation, we generate a state space without loss of any information of 500 states, and we analyze this in 0.015 seconds. And notice this result is exact, no approximation. So how do we do this? Now, there are a lot of techniques under the hood, and this has been worked by others. For instance, don't care propagation, already used by Boujou in other models, symmetry reduction. So basically, you look at the symmetries in the tree and try to exploit this. Modularization, which is a well-known technique developed by Dugan again in the mid-90s. And we complemented this with 3 new techniques, in particular rewriting. That means you try to simplify a dynamic fault tree before you analyze this. And the way to think about this is that if you would have a static fault tree is a Boolean formula, and a Boolean formula you can also simplify. Now, dynamic fault trees is more complicated, but you can do similar kind of techniques. And we use a technique called partial state space generation. And all this together, basically, all these techniques were revised, we improved them, and we actually combined them. So the partial state space generation, I only have one picture on one technique, which is this technique that we developed about 3-4 years ago. Where the idea is that you take a fault tree here on the left top, you take the reliability measure over here, and written down here as a temporal formula, but that's not so important. And now what we do, we're not going to generate the state space completely. but we're also basically going to generate only a partial, so only a fragment of the state space. And now you can give a very optimistic and a pessimistic view. In the optimistic view, you say, okay, assume now in the partial state space that everything already will never fail again. And you can take a pessimistic view in which you say, assume in your partial state space that basically everything will immediately now fail. And you can understand that this gives you an upper and a lower bound on the reliability measure. And that's what you see here in the interval. And now if the interval is close enough, if that's precise enough, you're finished. If not, then actually you go back and you refine, and refine means you further develop your partial state space. And this turns out to be a very simple but very effective technique to analyze huge fault trees. So here I give you some examples. So there is a publicly available benchmark suite, FWAT. We looked at measures like standard unreliability and mean time to failure. There are roughly 400 benchmarks, and we compared the tool to 2 existing tools for DFTs. And both these existing tools are, let's say, way better than the original tool by Dugan Galileo. In particular, DFT Calc, it has been developed. It's a similar technique as we do, but I would say less efficient. And there is a tool that does simulation, in particular rare event simulation, that recently has been developed in order to, let's say, be able to treat events that happen with a very low probability. And we used it we run it on a standard machine. And this is the way it looks like. And this is a cactus plot that says on the x-axis the number of benchmarks that you solve in a certain amount of time. And a certain amount of time is indicated on the y-axis. So you see the simulation tool, which is the green curve completely on the left, which is the rare event thing, which apparently comes with quite some overhead. You have to do many simulations, for instance, in order to get results with an accuracy of 10 to the power minus 4. The DFT calc is over here, and you see that the optimized state space generation techniques that I mentioned before gives you an enormous boost in the number of benchmarks that you can solve. So actually, it means that you can solve more benchmarks in 1 second than the other tools can handle in 1 hour. And this, I think, is a drastic improvement that has been, let's say, delivered over the last couple of years. Now, you may ask yourself, if a DFT contains many static parts, can you then also use, for instance, BDD techniques? And yes, this is the case. So here I brought you an example. You see an example of a dynamic fault tree on the left. It's pretty static because you see that, for instance, elements T and K and G are all static. And it has basically 2 dynamic subtrees indicated in the dashed boxes here. And what we're going to do is we're going to use our state space generation technique to analyze, for instance, the mean time to failure of those dashed boxes. That means in principle that in the tree, we just replace those subtrees by just leaves here, what you see here in the middle picture, H prime and S prime. And now the remainder is just a static fault tree, and the static fault tree can be analyzed by using BDDs, as I explained to you before, and this can be done very efficiently. In order to show you what that brings, we looked at many different examples from railway, from vehicle guidance, the autonomy case that I'm mentioning later, and all the examples from the benchmarks. Here you see the number of static gates, and maybe here you see the number of dynamic gates involved. The last 2 columns are actually after you have initialized, after you have detected all the, let's say, the dashed boxes, the modules, then these are the numbers. So what do you get? Again, same kind of log scale pictures. You should interpret the BDD, the combination of the BDD technique with the other technique on the y-axis. And if you would do the plain Markov chain analysis technique, that's on the x-axis. I'm looking at the picture on the left, by the way. All the runtimes are in seconds. And what you see is that for many case studies, you are up to orders of magnitude faster by using a combination of the BDDs and this very slim, let's say, state space generation techniques. The picture on the right, I'm going to ignore for the moment. And that means that actually, if you combine BDD analysis with this Markov chain analysis, this outperforms if you would do only Markov chain analysis, and it only also if you would do Markov chain analysis with modularization, even that is outperformed drastically by this technique. Good. I come to part 4, the industrial case studies. I brought you 3 case studies that we carried out in close cooperation with industrial partners. So the first one is criticality assessment of railway infrastructures. And you see on the top of the slide, this all has been recently published. So here you see a plan of a railway infrastructure. You see here axle counters to release the routes. You see here switches. I mean, think about crossings, but also think about slip switches. Here there are some signals. Here these vertical lines are basically tracks. And what do you need to do? You basically think about this as a path. Look at the red indicated path. The train comes from the left. It enters, for instance, a railway station, and it needs to leave the railway station, and that is on the right of the slide. Now, and that is what is called a train path. So we will need to establish a train path that routes the train basically from the entrance on the left to the exit on the right. All the field elements, so the axle counters, but in particular the switches, they need to be operational. And they also, like switches, need to be in the correct position. Good. So what is at stake here? I mean, elements can fail, they can be in the wrong position, etc. And this is something that you would like to model. So what we developed for the German railway is actually a tool that takes as input infrastructure data. So basically those plans. Then we looked at train routes that we obtained basically from the scheduling. And we modeled several field elements. So we explicitly modeled axle counters, switches by means of fault trees. So think about here that we have a fault tree for the whole railway station. We have a whole fault tree for each field element. And now for a whole station, you can complete this. So you get a complete dynamic fault tree that models all possible routes in the station, plus all possible failures of all the involved components. And this fault tree can then be analyzed using the techniques I explained to you before, using, for instance, the storm model check. Good. So how does it work? I here brought you some examples. I brought you examples from 3 different railways. You see them on the left: Aachen, Herzogenrath, which is a village outside of Aachen, and Mönchengladbach. I mean, it's fair to say that Aachen and Mönchengladbach are the largest ones. And you also see that in terms of the numbers. So for Aachen, for instance, here you see in this model, which is the standard variant, that you have 61 route sets, about 60 routes, about 60 possible train connect paths. So you have 60 possible routes, and there are about 50 different components: switches, axle counters, signals, and so forth. And similarly for the other model. Now, we all model this by fault trees. So here you see the size of these fault trees and the Markov chains. So here is the fault tree. I should say that those fault trees are automatically generated, right? What we provided together with the railway engineers, because they, of course, had, let's say, the application knowledge, was to model the switches and the trains, the train routes, and so forth. But once we had this, then we could just take basically the plan of the railway station. You see such an example of a plan here on the left. And this is input as a text format into the tool, and the fault tree is automatically generated. You also see in particular, and I would like to emphasize this in the 3rd column, number of dynamic, that there are quite a couple of dynamic elements to model this. And if you convert this into a Markov chain, you see you get Markov chains of sometimes millions of states and even millions of transitions. And of course, you need to be a bit patient to build these kind of Markov chains. You can take about 2000 seconds, but in the end, then you can analyze them. And also those Markov chains are automatically generated. And then what you get in the end, and this is the way we presented it to the end user, you get pictures like this, and they are kind of a heat map, where you see again on a very abstract level, the plan of a railway station, in this example, Mönchengladbach. And for each element, the criticality computed by, for instance, the Birnbaum index is indicated for each element. The more red, the more critical. The less red, the less critical. And you can even do this more detailed. You can even look at switches, and you can even, let's say here you see the slip switch, which is, let's say, divided into 4 parts. And you can even indicate for each of those parts, what is the criticality. So here, for instance, you see the criticality where the left part is, let's say, less critical, but the right part is more critical. And these are the kind of things that you now completely automatically can compute from infrastructure platform data from railway stations. And this is an example of DFT analysis. The second example I bring you is one on autonomous vehicles. And this is a case study we carried out together with BMW in Munich. So here it's clear, right? The major safety goal is to avoid the wrong vehicle guidance. And I guess you know that there are those ASIL levels, and they were interested in BMW in ASIL level D. And ASIL level D means that about 10 to the power minus 8 residual hardware failures per hour can happen. So the problem they confronted us with was the following. They provided us several what they call functional safety blocks. I don't have time to go in all the details here, but this you can think about this as software. This is modeling the different components in your vehicle. So EP is the environment perception, TP is the trajectory planning, and AM is here the actuator management. So S are a couple of sensors on the left, and there are a couple of actuators on the right. Okay, and now they have different kind of architectures or different kind of configurations depending on the kind of safety level. So here you see a classical TMR kind of thing where you just tripled this whole sequence, this whole chain of EP, TP, and AM, and then you add a voter to it. But their most sophisticated thing is like over here, like you see in picture D, where you have an EP and a TP, and then you have a switch, and only then you have the AM, and then the EP and TP can also have a fallback version of it, and these are indicated over there. So that's not as expensive as a triple modular redundancy thing, but it's still, let's say, hopefully using this fallback part, it can safely guide your vehicle. So this was one input, these pictures. And secondly, the BMW gave us examples of car architectures. And they are, of course, at a very abstract level, but think about this as hardware architectures. Now you see example here on the left, where you see, again, sensors on the left and actuators on the right, and also one actuator on the left, by the way. You see this advanced driver assistance system. You see several electronic control units, and there is one bus. In the second architecture, you see that the bus has been duplicated in order to be, let's say, redundant, right? And you see that also the ADS has been actually triple modular redundant. And here you see on the right another architecture where actually there are two buses again, and now there is one standard ADS and one which is more advanced, which is what the plus indicates there. And the question was basically, given these architectures and given these software, how can you, let's say, what is the optimal mapping of your software system on the hardware such that the safety is as good as possible? So this is basically the picture. Here you have, here you have the software. So these different kind of architectures here, those different kind of configurations. And here you have the hardware. And the question is basically how to optimally map the software on the hardware. So what we did is BMW was interested in various reliability metrics. And this is maybe an important slide because it indicates that they were interested in reliability metrics that go beyond the standard thing. I mean, the first question, how probable is it that the system is fully functional at time t, is a standard reliability question, right? But for instance, question 2 already, what is the fraction of failures without being degraded first, is already another fraction. Or what is, let's say, criticality, number 4. How likely is it to fail within a drive cycle after some of the components already are in degraded mode? Yeah, so these are going beyond the standard reliability metrics, and these were the questions they were interested in. We modeled them in temporal logic. I will only include the slide for completion, but I'm not going to explain the details here. Here you see some statistics. So we looked at different architectures, different scenarios with different numbers of sensors and different numbers of activators. We modeled them as a dynamic fault tree. We generated the state space. And what you see, for instance, in the last column is the percentage of degraded, let's say, mode states in the whole model. And this has been analyzed. And then you get pictures like this, that, for instance, here you see on the left, the sensitivity. So here's the failure probability on the y-axis and the amount of time that has elapsed in hours on the x-axis. And then you see for different, let's say, different mappings and different scenarios, you see that, for instance, this green mapping, which apparently is 3/C, with the details on the previous slide, is actually, according to this measure, the optimal, let's say, mapping for that safety, for that reliability metric. And similar on the picture on the right, it says something about what is the integrity after the system has degraded. And also there you see that, again, the green triangled, let's say, mapping, as well as the blue one, are performing significantly better than, for instance, the red one. So these are the kind of information that you can get analyzing these filters. My last example, and then we go to the demo, is a nuclear power plant. And this is a case study we recently did with a French company, Électricité de France. So ADF, Électricité de France, is the largest energy provider in France. And they proposed in 2017, you see the citation here on the top of the slide, a case study. And basically they challenged the reliability community to basically faithfully model their emergency power supply of the nuclear power plant and to verify, so to compute metrics like reliability, MTTF, and so forth. Now, it's important to understand that this is a highly complex and safety, of course, very safety critical system. As we're going to see in a minute, it has multiple power sources. The problem with computation is there is a large difference between the failure rates. So you have components with a very low failure rate and components with a very high failure rate. The components may fail due to common cause failures. On-demand failures are present. There are circular dependencies and there are multi-directional interactions. So it's a complex case study proposed in 2017 as a kind of a challenge. And we try to tackle this challenge together in cooperation with the people from EDF. And here you see, by the way, a kind of a scheme of this electric power supply. So here you see the nuclear power plant. And this whole scheme is basically the power supply. So the plant can either get supply from the bus bar on the left or the bus bar on the right. You see that there is quite some redundancy. If you look carefully, the two boxes now in the red boxes on the left and on the right are basically redundant. And even, for instance, for the LHA on the left, you see that standardly it uses the LGD, which is another bus bar, as power supply. But if that fails, and that's indicated by this red dashed arrow, then actually the diesel generator will take over. And if that also fails, then there is even a turbine generator. So there is three different, let's say, power sources. On the right, you see that there only have two possible power sources. So these dashed lines are reconfigurations. So here, basically, the grid feeds is the standard power supply. But if the grid fails, you can still use the unit. And if the unit fails, you can still use the TS and the TA. And if the TA fails, you can still use TS. So there are a lot of redundancy, there are complex interactions between the components and so forth. We modeled this in 2019 as a dynamic fault tree. You see it here, it's very hard to read probably, but you can find the reference on the top of the slide if you are interested in the details. It has about 200 elements, the whole tree, and about a quarter of them are dynamic gates. And that I would like to emphasize. So here you see some statistics, maybe that's not so very relevant. But what is very important is the following. This cannot be adequately modeled by static fault trees. There are so many dynamic elements present there, and there's so many common cause failures, temporal orderings, and so forth. You cannot model this by a static fault tree in an adequate manner. So here you see some evaluation results by Storm. This paper published in 2021. And what I would like to emphasize is here is the precision. So that tells you up to how many decimals the result that you compute is accurate. And notice that you partially generate the state space. So for instance, in the very first row that you see, where the case with 100 hours, which is the mission time, you see two entries, and they basically only differ in their precision. In one is the precision is 8 decimals, the other one is 9. And you see that in order to get a precision of 9 decimals, you have to basically generate 4 times a state space, which is 4 times as big as the state space for 8 decimals. And this is the partial state space generation, and this is the non-repairable case, and this is the repairable case. So what you see here is that even for millions of states, you are able to, let's say, analyze this in a matter of minutes. Good. Now, Before I conclude, you might ask yourself, nah, that's maybe all nice, but why can you not use just simulation, right? You just use a standard discrete event simulation, and then you can also analyze these kind of Markov chains, right? Or fault trees directly. And true, that is the case. And of course, there are pros and cons for both. I'm not going through all of them. The main point for the model checking thing is the state space explosion, but we have seen that there are clever techniques to combat that. Computability, I mean that you, of course, need to make certain assumptions, otherwise things are not, let's say, computable. So for all the fault trees I mentioned, all the failure rates are negative exponential, and you basically analyze abstract models. Now, for simulation is, of course, insensitive to the state space, because you only need to know the current state. That you can deal with very expressive models, but it's biased to certain scenarios. And the last point I like to add is the high precision, high cost. If you would like to get results up to, let's say, 10, 12, 14 decimals correct, it needs many simulations. Good. And my argument, I'm going to substantiate this with some results, is that model checking provides better precision than simulation. And we did this again with EDF, with this French company, because this French company had a simulation tool for their model. They actually don't use DFTs. They use a slight variation of them called Boolean logic-driven Markov processes, but the whole idea is the same. So we compared different models, and you see the models on the left. These were the benchmarks provided by them. You see again the number of states and the number of transitions in these two things. And then we basically compared the simulation time. So YAMS is a dedicated simulation tool for reliability. So it's not an off-the-shelf discrete event simulator, it's really tailored. And you see actually that, yeah, for certain models, you need quite a bit of time. Whereas if you compare this to the model checking time, yeah, you see that sometimes model checking is way faster. Here you see, for instance, 10 minutes compared to 1 hour simulation. Sometimes it's also the other way around, right? I mean, where do I see that? No, there are not so many examples here, but here, for instance, here you see 43 minutes for the model checking and simulation is a bit faster. Yeah? But in general, you see that actually in many cases, this technique that I explained to you is actually faster or competitive to simulation. Here you see something about the precision. You see different models on the x-axis. These are the models that I just showed you on the previous slide, plus some extra ones. And you see the relative error on the y-axis. So 0 means error is 0. And we compared doing simulations, 10 million different simulations, to, let's say, doing the model checking with Storm with a precision of 3 decimals, which admittedly is very low. I mean, typically the default setting is something like 5 or 6 decimals. And then what you see is here on in orange, the, let's say, the deviation or the, let's say, the error, the relative error by simulation. And in the blue bars, you see the relative error of the model checking. And you see immediately the difference, right? So EDF, after working with them for 4 years, concluded that probabilistic model checking, the technique that I try to advocate in this talk, provides better precision, and it supports metrics that go beyond standard reliability, availability, and MTTF. What are the take-home messages? And then we go to the demo. I showed you that you can analyze the largest dynamic fault trees ever, that you can analyze metrics that go beyond standard reliability measures. This is fully automated, and it has been validated by various industrial case studies. What are the tricks behind it? Basically 2 things: a very effective and very many optimization techniques to do the state space generation. And we used efficient Markov chain model checking techniques. And you should take into account that these model checking techniques, I did not explain you the details, have been developed over the last 2 decades. So there's have been a lot of effort, let's say, put into this. And if you're interested, you are more than welcome to download the tool and try it out. And now I hand over to my next speaker, Falak Sher, who is going to demo using the brand new user interface, the tool Storm.
Thank you, Jasper. Okay, Now I'm going to give a demo of the user interface that we have built on top of Storm model checker. So in this demo, we are going to present you a case study that Peter just presented you about the nuclear reactor. So let me first load the DFT that have been built for this case study. Okay, so this is the level of the complexity that you can observe from the size of the DFT. So I cannot go deep into the element level and explain you which component models, which thing, but you just have to trust me that this is the model that we build for the case study that Peter just presented to you. So now, so for this model, I first show you how to verify certain properties. Like for example, these are these two standard properties that people measure. One is the mean time to failure. So I come here and I analyze this with Storm model checker. So when I verify this model, so there are two steps that are done. In the first step, we convert the DFT into a Markov chain, and this is called model building step. And once the model is ready, then we do the model checking step, in which we verify this property like mean time to failure. So it will take around 1 minute or so to verify this property, because time will also be spent on model building and then model checking of the property. Okay, so here's the result. So you can see that around 20K hours is the mean time to failure for this model. If you click over here, output, you can see the number of dynamic gates, basic gates, and total number of elements, and the size of the CTMC, which is generated by the model checker Storm, and the time it computes to do different approximation techniques and the model checking. It just took 0.002 seconds. The total, it took 37 seconds. Okay. Okay, now the next property is that I want to measure the reliability of this model. So I do this reliability analysis for 10,000 hours. So in 10,000 hours, what will be the reliability of this model? You can have it filling in just half a second or so. Okay, so after 10,000 hours, the reliability of the system is 0.63. Okay, good. Now these are the basic properties that you verify, but let me show you how we can verify certain properties which are a bit complex. So if you go back to this screen here, you see that the model is quite big. So, and every node, every gate in this model basically represents some event. So sometimes you are not interested in all of the events. And here I show you how we can specify certain events which are relevant to us or in which we are interested. For example, in this model, there are two batteries which are working as a secondary energy source to provide electricity to circuit breakers. So one is the battery B. So I just gave it a new name, simplified name, battery failure B. And there is another component, there is another battery, battery A. I also give it a new name, battery A. So these are the two batteries that we have in our system. Now I'm interested to in a situation where both of the batteries got failed. So I define a complex mode, which I call battery failure, and I say that battery A fails and as well as battery B fail. So I just want to point out that here you can write any Boolean logic equation on these basic events that you have defined. Okay, so I am defining a situation in which I am interested in a situation where both battery A as well as battery B fails. Okay, now this is the complex scenario. Now I define properties that I can verify when my system, in which my system, both of the batteries of my system got failed. So let me show you a property which is failure under limited operation in degradation. So this property basically, so this, if you look at the formula, this property basically calculates the probability of failure from the initial state within a t time bound to a state where your system degrades. And then from the degraded state, you calculate the probability of the system failure within this drive cycle. Okay. Now I go to verification. Here, this is the property that I have just added. I click verify. Here I select the mode in which I assume my system failures. So I'm interested in this mode where my battery fails. And this I want to verify in 300 time units, for example, and I give the drive cycle of 20 hours. Okay. Okay, so this I verify. Again, it will take a bit time because we are going to perform two steps. Number one is the model building step, because we have defined new system modes in which we are interested. And in the second step, the probability will be calculated. So it will take around 3-4 minutes. So let me show you some more features of this tool. So let me go back to this tab where I can define properties. So if I click over here at properties link, so you can see that there are some predefined properties and there are some custom properties. So these predefined properties are the ones that we calculated for the case study that we did with the BMW about the autonomous driving system. And here, if you click on custom, you can write any CSL logic based query over here. For example, I am interested in a situation. For example, let me give it a name, a property, let's assume A. I define a variable, for example, time, and here I write a formula. For example, I'm interested in what is the maximum probability that I start from the initial state, and within, for example, t time units, I end up into a state where my battery A fails. Okay, so this is how I can define any CSL based logic query over here, and I can verify that property later on once I go to this verification tab. Okay, this property, fluid property, it's still running. Let me show you another feature, important feature of this tool, which is simulation. So if I click over here, so what you see is the this is the dynamic fault tree of this case study. Now I want to do some sort of simulation. So let me start the simulation. Okay. Now you can see that there are some basic events which are in green color. So those basic events can fail at any time. So let me fail some event. Let me click on this one. So I just click on this one, and now this event has failed. And because of this failure, this gate has also failed. And these yellow events, now they are in don't care state. Okay. Now all other green events, again, any one of them can fail at any time. So let me fail this one. So now these two events are just failable. Let me click this one. Now this is the only event which is failable. I click here. Again, other events are now failable. Let me fail this one. Now let me click here, here. So I will just keep on clicking, making this failure till my top event fails. Okay. Now, if I click at this event logs tab, so here you can see the basic events that fail in this specific order till the time my top event fails. Okay, so this is how you can interactively play. Sorry, one still this is active. Let me click this one and this one and this one, and now this top event fails. So this is the list of the events, basic events that fail in this specific order, fail so that my top event fails. Okay, now let me go back to this verification. It's again running. I think it will take just 1-2 minutes, and then I will go to experiments tab and will show you how we can perform different experiments using this tool.
I think you have about 2 minutes left, Palak.
Yeah, it's just 2 minutes. I need more. I just want to give a little bit feeling of experiments after this. I should have this. It's taking a bit time.
I think we should continue, Falak. I mean, that's.
Stop it. Okay, let me stop it and then I show you experiments. So here, what we can do is that we can also perform experiments. So let me select this property, and I am interested in this battery failure mode, and I give you a feeling. I start from 0 time and I end up in 300 hours with the 100 time step, and drive cycle of 0 with 40. So let me do this for reliability then. Okay, so I can give you a feeling of reliability of the system, and let's see. 1000 hours. Okay. This will give you a feeling how reliability of the system changes with the passage of time.
Good. Your screen is gone, Falak. And I think we should stop. I mean, it's 1 hour.
I think we can stop. it will take a bit time to generate the results, or maybe we can start QA session, and if results comes, so I can show them.
Okay.
Yeah.
Then thank you for your attendance, and thank you for listening, and we're more than welcome to pose any questions.
Well, once again, thank you for sharing an exciting topic. I look at this and it's just like, gee, my God, how lovely to see the new tools coming out. There are a few questions coming in, and I hope we can get some insight of this. When we model fault trees, I'm more on the preliminary area. We usually would try to make other engineers to do it rather than having a small unit within a large organization to do this. So how easy or how difficult is it to train up an engineer who may have very little background in fault tree analysis to understand and use your tool?
That's a question. We did not do any, let's say, pilots with industrial partners yet, because the GUI that Falak just presented is actually has been developed. But it's something that we plan to do. So then I can tell you more. But I can tell you at least that the experiences of Électricité de France, they are using, as I said, similar things like dynamic fault trees, and there are hundreds of engineers that are trained and that are using those DFT-like fault trees on a daily basis. And what Falak was showing was more the advanced level of the tool. The tool will also have a simplified version so that, let's say, engineers without, let's say, deep knowledge about the underlying technology are also able to apply the tool.
That will be important, because I find out most of the users will just leave all the setting in default mode rather than dig deep into it.
I fully agree.
Yeah, that's difficulty of non-expert running your expert program. Other question coming in is when we use a static fault tree analysis, we usually can generate uncertainty propagation for parameters. For example, failure rate, we could input a distribution rather than a single value, because in risk analysis, we usually want to look at uncertainty band of each parameter affecting the top event distributions. How is that going to handle by this dynamic fault tree model? Because in order to do the Monte Carlo simulation for, let's say, 1,000 run, we need to have a fault tree relatively running fast, so we could propagate many rounds of simulations to see the uncertainty being propagated from the basic event to top event. How will you handle this uncertainty mode?
I'm not exactly sure whether I understand the question, but so is it the case that you would like to change the failure rates of certain components during the analysis?
No, it's the case that back in the old days, we usually will represent the failure rate of a basic event with a distribution rather than a single number. And we will use a single number as a mean value. And so, for example, failure of a pump, you could have 4.5 times 10 to the power minus 5 per hour. But we will input a distribution. It could be uniform, could be different shapes to represent the actual incoming data. So we'll look at the distribution of the top event to look at how confident we are within the probability of propagation. If we have a bunch of uncertain input on the basic event, then the output of the top event will also show a large uncertainty band rather than a narrow uncertainty band. Then we'll look at the confidence level or our confidence in the analysis.
Okay, I understand. Yeah. So what I showed you in the talk are all based on mean values for negative exponential distributions. Right. Now, if you want to know, let's say, the uncertainty, so suppose you take the same mean values, but you would like to know what happens with a uniform distribution. What you can do is you can model, approximate this uniform distribution by a phase type distribution, and then model this as the distribution inside, let's say, a leaf of the fault tree, and then apply the same analysis technique.
Yeah, sounds good. One last question coming in is asking about when we do risk assessment, we usually will also use the event tree method to handle different alignment of maintenance or redundancy current mode failure, which is a lot easier to handle in the event tree level. How would this dynamic fault tree model couple with an event tree in a large scale risk assessment?
So what you can do is, I understand that the question is also a bit, where do you get those dynamic fault trees from if you do a large scale safety analysis of a system, right?
Or using event tree model?
Yeah, of an event tree model. So what we're currently automating is actually the automated generation of those dynamic fault trees from SysML models, which are models used in the in software for software modeling, and that's our kind of models. So that allows you to obtain dynamic fault trees basically in an automated way using some annotations in your software model, and then you can generate push button those dynamic fault trees.
Okay, there's a more practical question coming in, is about, is the tool free to use? We all want free stuff. And additionally, can we create fault tree within the tools, or we only import like fault tree model or Boolean algebra equations?
So the tool is, the Storm model checker is freely available. It's publicly available. It's even open access. So everybody can download the tool. The link was on my last slide. The tool that Falak presented was the GUI that is built on top of Storm, right? And there you can input the fault tree. You can even click and you can draw the fault tree. The model, if you just use plain Storm without the GUI, there are textual, let's say, formats in which you can describe, for instance, the Galileo format that are supported by Storm. So then you can describe a fault tree in that format, and then you run Storm.
Good. A question from a young member. How and where can we start learning the techniques of performing such reliability analysis simulation as a newbie or newcomer on fault tree analysis? By studying under you?
Yeah, well, that's definitely a good possibility. Do an internship in my group. No, I'm kidding. But there are, of course, publications, and I indicated all the links, all the publications on my slides, which I will make available. And there are also, I would say, in my case, 2 PhD dissertations. One is coming up soon to be defended in October. The other one has been defended last year. And they contain, let's say, all the algorithmic details, many more experience that I showed you here. So if you really want to know what is under the hood, then there is indeed a lot of literature that you that I can offer you. Yeah.
Yeah, I guess the only way is to get your hands dirty and dig deep into the hood. Well, the time is running out now. I see that Alan has put up a message asking participants to fill in a post-event survey. Please help us to do the survey. And also, last but not least, thanks very much to the speakers for your valuable time and sharing your knowledge and experience with us on this exciting new topic, to us in Hong Kong at least. And also thank you for the participants, co-organizing committees, and also the supporting organizations to make